Move on to problem number 6. All right. Let me ask you a question. What's the meaning of the ionization energy? What's the meaning of the ionization energy of an atom? Okay, so what's ionization energy mean? We discussed that before, right? So what's ionization energy?
That'd be how much energy it takes to get the charge off the atom.
All right, give yourself 5 points. That's the amount of energy required to liberate an electron from an atom. That's it. All right, so how do we figure that out? What do we have to do in order to figure out the ionization energy of the hydrogen atom? So what does it take? How much energy does it take to actually remove this electron from the hydrogen atom? All right, so what does it say? You know the radial distance, which is going to be half an angstrom that you're looking at. You know the value of the charge. So how do you figure out the amount of energy required to remove an electron from that atom? How does that go? All right, let's do this problem. This is the standard problem. Anything and everything related to the hydrogen atom is something we will focus on, so you can see the evolution of physics through the hydrogen atom. Those of you guys who are getting into chemistry, electrical engineering, chemical engineering, material science, you will have to take modern physics. All right,
so the ionization energy of the hydrogen atom. So let's what's given. We got the radius. We are looking for the ionization energy in terms of electron volts. Net charge, positive and negative. Unit charge will have the same value. We're given the mass of the electron. So the question is, what is the ionization energy? What's the meaning of it? Ionization energy simply means the amount of energy required to knock an electron out of the atom. That's it. Now, looking at the location of the electron, which is within the reach of the electric field at a radial distance, which means that the electron has potential energy, and because it's moving, it's also got kinetic energy. So I'm going to use wiggly E for the mechanical energy of the charge. Mechanical energy of the electron is the same as the ionization energy of the electron. So we have to provide this amount of energy to the electron in order to knock it out of an atom. So we get an expression for the kinetic energy as well as the potential energy. Potential within the potential energy is the potential of the positive charge, which is right at the center. So it's K divided by R. All right, check to see what we got numbers for. We got numbers for everything except for the speed, so which means that we have to figure out what the speed is. And we know this is circular motion, so which means that there's a centripetal force involved. And we know the centripetal force is the electrostatic force. So equate those to each other. And then just cancel the like terms. And notice that on the left-hand side, if you divide the left-hand side and right-hand side by 1/2, it's going to give you the kinetic energy term. So the term on the right is going to represent the kinetic energy, which looks like electric potential energy. All right, so the final energy is going to look like 1/2 of the potential energy of the electron, except there's a negative sign up front. I'm going to pull one of the e's out, and the term on the right divided by 2 is going to be half the potential energy of the electron. That's going to be 13.58 electron. It's volts. Pull E into the unit system, so all of a sudden it becomes EV. So we're good with that. It's a nice little trick. Now we have to worry about the negative sign. What's the meaning of the negative sign? We end up getting the negative sign in terms of the potential energy of the electron, which involves a positive and negative charge. Now, in that case, the negative charge implies that there's an attractive force between the charges. So if you see a negative charge, which simply means that, hey, let's say some kind of a potential well, attractive potential well. If it's negative, which means it's a potential well, which means that the charge is captured by the atom. So, which means that that's the amount of energy that you have to supply the electron in order to free it from that potential well. Which means that that's the amount of energy required to free.
Okay, let's move forward. All right, so here's the main observation.
In Glenview, high winds took down a power line, trapping a woman inside her car.
The car is part of the circuit. It's electrified.
Police.
She can touch the outside of the car. She can touch.
Did not
She can touch the metal on the inside, she's fine. She can touch the
No,
metal
the wire was-
outside. She's still fine. Okay. So why is it that she can touch the metal outside and she's going to be 100% fine? I think Matthew is the one who came up with the best explanations. He said, because the strength of the electric field on the inside is going to be 0. The net charge on the inside is 0. The strength of the electric field on the inside is 0. Oh, so what does it mean? What that means is the following, guys. All right, so these are I gave you guys these lecture notes. Okay, let me check to see what it is. This is lecture 18, lecture notes, or this is a lower level class. The math is not thick, so you can get to the physics of it. All right, guys, it's a hollow conductor that you're looking at. Boom, 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 boom. All right, so let's take a look at the difference, voltage and potential difference between inside, this is the inside, and this is the surface. So we'll take a look at the voltage difference. Voltage difference between inside and the surface depends on the electric field between these 2 points, right? So what is the strength of the electric field inside a metallic container? It's going to be 0. If the strength of the electric field on this inside is 0, if this is 0, what happens to the voltage difference?
0.
The difference is going to be 0. All right, so which means that the surface and inside, they will be at the same voltage or potential. Guys, if there's no voltage difference, there's no reason for the charges to move. Remember, charges will always go from higher potential towards lower potential, right? So the inside of a metallic container is exactly at the same voltage as the surface. So between the surface and the inside, there's no voltage or potential difference. But if there's no voltage or potential difference, there's nothing for charges to go through you. That's what it means. All right, I kind of fumbled it a little bit, but let's go forward. All right, so once the equilibrium has been established, the excess charge placed on an insulated conductor will be found to lie entirely on the surface. So we knew that. So this is true even if the conductor is an empty internal cavity. So this is what happens if you grab stuff from a physics book. Okay, so between the inside and the surface, there's no voltage or potential difference. And once you get outside, it's going to act like a point charge, which means that the voltage or potential is going to. On the inside, the electric field is 0. Okay, so within this distance, the electric field is 0, so there's no voltage or potential difference between those 2 points. As the electric field diminishes inversely as the square of the distance, the voltage is going to diminish as inversely as the radial distance. Yeah, that took a lot. All right, what's the best answer? Whenever you guys are ready, just jump in.
0.
All right.
Thank you, 0.
Okay, so most of you guys will say 0. Okay, 0 is not the best answer, so I'm going to give you guys 2 points for going with your gut.
Isn't potential, like, doesn't it require 2 points to measure between?
Okay, very good. So what do you suppose the best answer is? Okay, so what does it say? It's a hollow metal sphere is charged with a potential of B, right? So what's the potential at its center? Okay, guys, so the hollow metal sphere is charged with a potential of B, which means that right at the surface, the potential is going to be V. So what do you suppose the potential at the center is going to be?
It would be V because it's the same thing.
Right, give yourself 5 points, guys. There's no potential difference. The potential difference is 0, but which means that the inside potential is going to be the same as the outside potential. So if the outside is charged with potential B, the inside is going to be at the same potential. The best answer is going to be that. It's going to be B. Okay. Now you guys are ready. We're going to have real physics. To me, the physics.
Hello? Sorry, my meeting ran late. I should be home in about half an hour.
I wanted to grab it.
Sure, I can pick up dinner. What do you want? Hot and spicy. That's what I'm talking about. I will. I love you too. Whoa. Oh, man. So that's what an airbag feels like. My car. Great. I should probably get out and see how bad the damage is. Wait. Are those telephone wires or power lines? Either way, they could be hot. No way to be sure. Don't take any chances. Just stay in the car and call 911. Good thing I actually paid attention during that safety meeting. Hi, this is Stephen Stonebanks. I've been in a car accident. I hit a power pole. I'm on Highway 18, somewhere east of the 356th Street exit, a couple of miles. No, I'm okay, but there are power lines on my car. Okay, yeah, I know. I won't move until you tell me that the line is de-energized. Yes, I will stay put. Okay, please hurry. Thank you. Honey? Listen, I've been in an accident. I'm fine. I hit a power pole. The car is a mess, but I'm okay. Yeah, I've called 911. They're on their way. Oh no. Hey.
Are you okay?
Hey, stay back! No, don't come any closer. You could get shocked by the ground around these down power lines. Stay back about 35 feet and make sure no one else comes near.
Okay.
I've called 911. They're on their way. Thank you. Honey? No, I'm fine. No, don't worry. Yeah, the police are on their way. Yeah, all I've got to do now is sit and wait. Honey? I gotta call you back in a couple of minutes. Oh boy. Not good.
Oh my gosh.
Okay. Plan B. Exit the vehicle. But now I gotta worry about touch potential. Touch potential is risk of electrocution based on one part of the body touching an energized object like a car while simultaneously touching the ground. Electricity flows from the vehicle through the body and into the ground.
Touch potential is the potential difference, right? The charge will go from high voltage to low voltage, which means that there's going to be a very strong electric field through your body, pushing the charges.
Essentially making me into a human jumper cable, which would be bad. I gotta jump and land with both feet together.
Okay, there's no voltage or potential difference between inside and the outside of the car. This you could do. You could touch the outside of the car, no potential difference, no voltage difference. Nothing is going to push or force the charges across your body. You're 100% safe. All right, you cannot touch the ground in the car at the same time. The best thing to do, or one of the best things that you could do, is jump. Keep your legs together. Why do you have to keep your legs together?
Whew, okay.
Probably a voltage that's
Okay,
different
yeah.
across the ground.
The car is going to act like a point charge. Every time you step outward, there's going to be a potential difference between your contact points. So, which means that you got to keep your legs together.
Now, step potential.
You don't want to do that. All right. So this foot is at a lower voltage than this one is. So voltage difference means that the charges are going to force through your body.
Once the ground is energized, electrical current can travel through me if my feet are close together. Electrical current enters through one foot and out the other. The further apart my feet are, the greater my chances of getting shocked. So I must move away using short, shuffling steps. Shuffle, shuffle, shuffle. There you go. You got this, Steven. No large steps. Just keep on shuffling. Every day I'm shuffling. Oh. I'm sorry, I can't come to the phone right now. I'm busy trying to stay alive at the moment. Almost there.
Hi, honey. No, everything's okay. No, nobody got hurt today. Well, except the, Remember how we were talking about getting me a new car?
This is really one. This is the second one.
Most of the time, power lines stay safely out of our way,
Not as good as the
but
first one.
sometimes
It's not
storms
bad.
or accidents can knock down lines. If a power line falls across your car, you know what to do. If your car is still drivable, simply pull out from under the wire. If your car is disabled, the most important thing to do is to stay inside. Use your cell phone to call for help. Keep others away from the car. Only get out when utility workers tell you it's safe. Never touch the car and the ground at the same time. The only time you should get out is if there's imminent danger, like fire. Open the door fully. Do not step out. Stand on the metal framing of the car. Keep your hands close to your body to avoid touching the car and the ground at the same time. Slide your feet together. Hop off with both feet. Hop away from the car, keeping your feet together. At a safe distance, slowly spread your feet apart. If you feel a tingle, put your feet back together and hop further away. For EMC TV, hop off with both feet together.
Okay, the only problem that I have with hopping, if you lose your balance, is that going to be a problem? Depending upon which direction you fall, right? There may be a potential difference between the top of your body and the bottom. So that potentially you can get yourself hurt.
At a safe distance, slowly
If you can
spread your feet
hop,
apart.
right? Not a big deal.